Thank you. Pointer. Well, I'm glad to be back. I understand you guys have had a very active time. I was asked to give, I think, a survey, so I'll spend most 40 minutes reviewing what I think are the natural things that have emerged over the years. And then I'll spend the last 15 minutes explaining some recent developments, which I think have clarified a good number of things. So I'm talking about random matrix theory and the Zeta functions and more generally L functions. So I think you all are familiar with the Wigner ensemble and universality in that connection and the threefold way of Dyson. But actually, random matrix theory is really about a tenfold way. And these are the 10 symmetric spaces of Elie-Cartan. Each symmetric space in a certain in its standard realization, as I'll give you an example, gives a random matrix ensemble. His irreducible symmetric spaces, compact, I'll choose the compact forms. And also, since we, in this theory, let n go to infinity, the sporadic ones do not play a role. The realization that there are 10 of them but not 3 of them that may be important was forced on Nick Katz and myself in the 90s. We had no option to sort of incorporate them in the way in what we were trying to do, as you'll see in a second. Martin Zierenbauer observed the same phenomenon, that there aren't 3 but 10 such spaces, the tenfold way. And in fact, he had a statistical physics reason for looking at it in solid state physics. And in the last 3 or 4 years, they've become very popular in sort of string theory circles, and especially in connection with classification of what are called topological insulators and superconductors by Snyder et al., where the 10 symmetries emerge again. I prefer to use this thing. Except it doesn't work. How about this? That works. So let me be clear what these are. These are finite dimensional, though compact symmetric spaces. N will be going to infinity. The simplest example is just the unitary group. Now, any compact Lie group with it contains a bi-invariant metric relative to which it becomes a symmetric space. I'm talking about random matrix ensembles, so there will be matrices and there'll be a probability measure. The probability measure will just be the volume form on the symmetric space. So for something like a compact group like the unitary group, or SUN, it won't make much difference. This is just Haar measure on the unitary matrices, and that's what Dyson called circular unitary ensemble. Often you'll see it called Gaussian unitary ensemble, GUE, because that's if you're in a non-compact setting. He invented or introduced the circular ensembles in order to get compactness and avoid all issues of things escaping at infinity. So the model of the circular unitary ensemble is the pure one and the one that's most relevant. So I'm giving you 6 of the 10 families. There's the orthogonal family. So these will be unitary matrices which are also orthogonal. Everything here will be some realization as unitary matrices. So the orthogonal matrices are those which also satisfy A transpose A equals I. And we could have a special orthogonal group, in which case I break up to 11. That's kind of important for us rather than 10, because we very much want to distinguish the even SO and the odd SO. There's the symplectic case, which I'll call USP2N, which are all the unitary matrices which are further lying in this group, which satisfy that they preserve the symplectic form J. So these are 2n by 2n matrices such that A transpose J, A equals J. And these are all groups, and they come with this bi-invariant metric. Now, symmetric spaces are not just groups. They usually come as quotients of groups by certain subgroups. And the two that are the most famous ones besides CUE are COE, which is the unitary group divided by ON. So they are n by n matrices, which also satisfy the property that they are symmetric. So their transpose is themselves. And you can realize this as this quotient space by taking B goes to B transpose B, where B is a unitary matrix. The stabilizer will be ON. and the image will be this compact Riemannian symmetric space, which again comes with this volume invariant measure, which is the definition of the random ensemble. Another very important one is the circular symplectic ensemble, which is U2n divided by USP2n, which again can be realized as the n by n matrices, unitary matrices H, which satisfy that relation relative to the symplectic form J, and again can be identified as through a quotient map.
I'm sorry, Peter. What did you say about the GUE?
Okay. There's CUE, COE, and CSE. You're probably more familiar with GOUE, GOE, and GSE. Yeah. What Dyson did when you work with GUE, which is Hermitian n by n matrices, there are different ranges of eigenvalues, and you have to localize, and you have to look in the bulk and outside the bulk and near the edge. If I'm in the bulk, everything is modeled perfectly by the circular unitary ensemble, and then I don't have to worry about technicalities of the non-compactness of the space. This is for finite n. And of course, what random matrix theory is about is many things. I mean, there are very great formulae that you can find which are the source of many developments. But in terms of the spectra, which is, of course, what's connected, perhaps connected with zeta functions, we are interested in the distribution of the eigenvalues. And once we're in these compact situations, it's clear how these are normalized, and there are no more parameters and things or ranges to look at. This is the reason Dyson introduced these circular ensembles. There are 4 others which I won't write down. They are coming up, as I said, in physics, but the list is already rich enough for number theory. One of the things I want to explain is that in the theory of zeta functions, there's only 4 of the 10 that are important. And they're not the usual 3 that everybody talks about, CUE, COE. I want to clarify that. All right. The first 4 in Cartan's classification are called type 3. They are the compact groups. The compact Lie groups, classical groups. And those will play a very central role in everything I have to say. So the type 3 ones are the first 4 which are separated out there. All right, now, if there are 10 of them, sounds like the Bible, and there are 3. There's a threefold way of Dyson. What's the relation? And why has Dyson's threefold way been so successful? And the reason, perhaps the main reason, so these are these 3 of Dyson, is that if you look in the bulk, if you take a random A in any one of the ensembles I've shown you so far, let's call that ensemble En, and you take a random matrix in one of those ensembles, so all those matrices were unitary, they can be diagonalized. That's how you get to the eigenvalues in an obvious way. In the case of groups, it's kind of clear. So anyway, if you take a random A there, and you look at the eigenvalues which are not near +1 and -1, but are in the bulk. So the bulk means here away from plus or minus 1. Clearly at +1 and -1, something special is happening. If I look at SO odd, then 1 is always an eigenvalue of an odd real symmetric real orthogonal matrix, so something's different happening at 1. If I look at the eigenvalues away from plus or minus 1, in the bulk, as we like to say, then and I take the scaling limits, so I look at the local statistics, they become completely universal and collapse to only 3 families. So the 10 symmetric spaces in the bulk only give 3 symmetry types, and those are the 3 types of Dyson, which have nice classifications in Hamiltonians, that this would have no symmetry. COE is time reversal symmetry, and this is a more complicated symmetry, or the symplectic symmetry. As I said, in the topological insulators, they have some more charge, further symmetries, which give up to all 10 exactly, which is kind of pleasing from another point of view. Okay, so how do you prove such a thing? Because one of the central themes of this special year has been universality. I don't know what Mr. Yao told you, but he probably reduced everything to this case, right? This is a case in which the Gaussian orthogonal, or the CUE example, is universal for the Wigner matrices, but you don't recompute this case. This case, you show that everything is universal and equivalent to that case. Somebody had to compute what's happening in these cases. There's no basis here. This is a completely natural thing. The Wigner ensemble is somewhat unnatural because it's dependent on choosing a basis. Here, these are got automatic symmetries. So in the CUE and the COE and the CSE, the key way to compute all these things, there are more ways today, but is due to Gordon. He made the breakthrough. He introduced the theory of orthogonal polynomials in order to integrate out one variable at a time. So if you actually write down the distribution on the eigenvalues induced, so you take Haar measure or this invariant measure on one of these symmetric spaces, and you induce a measure on the eigenvalues, it's got a xi minus xj to the power beta, where beta is 1, 2, or 4. And in each of those cases, what he showed is how to use orthogonal polynomials to get rid of these interaction terms and get explicit answers. And then your problem becomes a question of asymptotics in orthogonal polynomials, which in the non-compact case can be quite difficult, but in the circular case is a pretty straightforward classical problems with Jacobi polynomials, sines, cosines, completely elementary. So I want to point out that Gordon is the guy who made the breakthrough. It's quite funny to read Wigner. Wigner in a 1968 Gibbs lecture at the AMS says Gordon is using this fancy mathematics because Wigner had a surmise which was incorrect. That's what Gordon showed. And he's using fancy mathematics. What he's using is classical orthogonal polynomials, a formula of Heine from 1870. And for Wigner to say this is fancy mathematics is quite striking. Anyway, if he looked a little more closely, he wouldn't have had any problem understanding it. It's straightforward. Dyson was very quick to use that to compute correlations. So the tools in these ensembles, which are these circular ensembles, even for the tenfold way of Dyson, of Cartan, are easy to deal with using techniques that exist, and this is done quite beautifully in a thesis of Duanez, where he explains this collapsing to these three, and he discusses the distribution in the bulk. He also discusses the distribution at the edge. Excuse me. So the statistics of the eigenvalues near 1 in any one of these ensembles is characteristic of those ensembles. So there will be 10 different answers, and they are quite different at this point 1. And the point 1 is a very central point in the theory of numbers. So I'm not highlighting it for nothing, because this is where all the action is somewhere in for the theory of zeta functions. So at the points there, and I'm only going to discuss the type 3 ones, which are those compact classical groups, which are the only ones, as I said, the highlight of this lecture is apparently that's the only thing that zeta functions know about, not COE, not CUE, but only CUE and the symplectic and orthogonal families. One can compute using Gordon's methods, which eventually reduce to Fredholm determinants, and then you can use numerical methods using Proloit spheroidals to draw these graphs. This was done by Rubinstein. This is in my book with cats. So for example, suppose I take a large unitary matrix and I ask, what's the distribution of the eigenvalue nearest to 1 when n goes to infinity as I go over the unitary matrices? And I rescale, there are n eigenvalues, so I rescale by n over 2 pi so that I get something which is now mean 1. This is the distribution for unitary. So there's no reason that the eigenvalue is not near 0. So there's no repulsion, as people like to say. On the other hand, if you look at a symplectic matrix, which is a very large size, compact USP2n, n is very large, and I look at the eigenvalue nearest to 1, its distribution looks like this. It's got repulsion to second order at the origin. That can be shown to satisfy a differential equation of Paine-Lavey 5. That's thanks to completely integrable systems that you can actually describe these curves, though these were computed numerically, as I said, by Rubinstein using Proloit spheroidals. And this is the even orthogonal. So even orthogonal, there's no eigenvalue at 1, so there's no reason that the eigenvalue shouldn't be close to 1. And it's quite remarkable from these methods that you get these exact answers, which if you just generated a random matrix and looked at the eigenvalue nearest 1, a large unitary matrix, it would look like that instantly. So it's very much a robust feature. So that's how you compute these, and it all goes back to these methods of orthogonal polynomials. All right, so as far as random matrix theory, the theory is sort of well set up there from the 60s. Okay, 68, Wigner was struggling to understand it, but after that, I think if he just read it, it would have been easy. Anyway, it was easy for Dyson, who quickly calculated all the relevant features and plays a role in what I'm about to say now, as you'll see. All right, so now let's turn to the theory of zeta functions and what they have to do. So I just have to go through the history a little bit here. Montgomery computed something called the pair correlation. I want to be very precise what this is and exactly what you compute and what's a theorem and what's a conjecture, because this is not all fluff. Okay, the Riemann zeta function is that. It's given in that form as a sum and that as a product. And as you know, Riemann showed what's still the best thing we know about it, analytic continuation and functional equation after you append its Archimedean factor, a gamma function, and pi to the minus s over 2. So the functional equation already means that if the zeros are to be looking like eigenvalues of a random matrix, whatever this matrix is, it's got a symmetry which GUE doesn't know. So there's something already there that's philosophically important. Anyway, let's write the zeros as a half plus I gamma j, the zeros of the completed function. They're all supposed to be on the line a half, so that the gammas are supposed to all be real. That's the Riemann hypothesis. To interpret everything that I will describe from here on out, you need to assume, it's best to assume the Riemann hypothesis. So every theorem that will be stated can be proved without assuming it, but to interpret it statistically, it's important the numbers are real. So why don't you just assume that, because I'm trying to understand the statistic. How are the zeros of zeta made? What are they? Are they random numbers? Are they random what? Or are they something that we should have a formula for, since they control so much about the theory of primes? So firstly, because of the functional equation, the zeros are symmetric. The imaginary parts of the zero, these gammas, are symmetric about 0. They're real, I'm assuming. The Riemann zeta function doesn't vanish at a half, so 0 is not a 0. And gamma 1, as Riemann already had computed, is about 14.1 something. It's rather large for an L function. Usually the zeros are much lower down. Now, what I want to do here, which is what Montgomery did, is to look at the high zeros, very high up at the zeros of zeta. And I want to look at the statistics, the local statistics between them. Now, if I want to look at the local statistics high up, they're going to get closer together, because Riemann already showed that the number of zeros between t and t plus 1 is about log t. So if I start looking at differences between these numbers, it will go to 0. So you rescale or unfold. All these things are always done properly at the right scale. So you multiply by log over 2 pi. That's the asymptotic law of Riemann for the number of zeros. And now these numbers, which I'm calling gamma j tilde, are roughly coming down every second. And now we can ask, what's the statistics between these numbers of the zeros of the Riemann zeta function? And Montgomery computed what is called, he didn't formulate it this way, but it's equivalent. This is a slightly cleaner version. Is he forms the following expression. Let me take a function which is rapidly decreasing and smooth. This is a test function, a Schwartz function. You can even pretend it's compact support. And let me look at all pairs of differences of the normalized zeros up to n of them. I look at the first n zeros and I sum over all the pairs. I only divide by n, not by n squared, even though I'm summing n squared numbers. And that's because I've now arranged them to be more or less have spacing 1. So I should expect that if phi is compact support or rapidly decreasing, that this is picking up a bounded number for each 0. And so I should only be dividing by n. That's called the pair correlation at up to height n of the zeros. And the remarkable thing is Montgomery was able to compute this. I will say a word about how he does that in a second, or how we do it. For functions whose Fourier transform has support between -1 and 1. Nobody's ever improved this range. So if he was Schwartz function, you put this very harsh condition on the Fourier transform. It's like you're computing a measure and you only can compute a certain number of moments. And there's a phase transition that happens. That's why it's hard, but in any range bigger than -1, 1. But nevertheless, he found a way to compute this pair correlation. That is, as n goes to infinity, it was properly normalized. This, he found, converges to the integral of phi. Again, some density that was quite mysterious to him. Not mysterious to people in this audience, but mysterious to him. 1 minus sine pi x over pi x squared dx. And he conjectured that this holds without restricting any conditions on phi hat. And that's called the Montgomery pair correlation conjecture, a beautiful idea which he was trying to use to prove there's no Siegel zero. Many people are still trying to use this idea. So far, it's never yielded anything as far as that goes. But it's yielded a lot in other directions. Odlyzko took Montgomery very seriously, and he computed 10 to the 20th zero in some of its nearest neighbors. And to see, is it true that the pair correlation looks like this density that you see there? And sure enough, and everything I'll tell you fits like it was made for it. There's no other process has ever mimicked these numbers as well. So there's your pair correlation. Here's the dots. Those are the numerical data near the 10 to the 20th zero. So it's very convincing. On seeing this, Dyson in 74, so Montgomery was 73, he made the observation, since I mentioned to you that Gaudin had introduced this method to compute the CUE correlations. Well, he didn't formulate the correlations. He computed all the nearest neighbor statistics in terms of Fredholm determinants. Dyson computed the correlations. They're more or less all equivalent to each other, as we understand today. But when Montgomery showed Dyson the answer, he said, ha-ha, that was the changing moment. Those are the distribution of the zeros. That pair correlation you've computed is something I've seen. It's CUE pair correlation, which he'd computed 10 years before. All right, and Odlyzko, when he was checking numerically, once you're doing the numerics, well, you could do numerics, and of course he was also checking the Riemann hypothesis was true around there. And had he found a zero off the line, he would have put everything down and just told you that. So, of course, those always pass. There's no question about the Riemann hypothesis, but there is something we're trying to learn once you're doing all this numerics, and he checked every aspect of this conjecture of what's now called the Montgomery-Dyson conjecture. That is that the high zeros follow a universal law, which is CUE. CUE. So remember, I've told you about these families, but why CUE? Now, Rudnick and I found a very easy proof of Montgomery's theorem, and we then decided to look at this conjecture that the zeros, there's not just the Riemann zeta function, they're Dirichlet L functions, they're L functions of automorphic forms, and these L functions have very complicated different statistics for their coefficients. I will get into that very vaguely at the end. But let me just make clear, there's nothing universal about the distribution of the coefficients defining these functions. So if the zeros are to be universal, it's got to be something, if you're going to do anything with the coefficients, there has to be something interesting going on here. In particular, we knew that if you go to GL2 forms, there are forms which are not, which are called dihedral and non-dihedral, for which the coefficients behave very differently. And our expectation then was that the zeros would behave differently, and that this whole thing is a red herring. We were convinced we're going to just put this under the rug, and that maybe the Riemann zeta function follows CUE, there's no question, but other ones will follow something else. So we compute the pair correlation in complete generality, and sure enough, it's all universally the same. Then we sat down and said we have to compute all correlations. It's got to show up somewhere. We computed all correlations for zeta in particular, and for all automorphic L functions on GLN. These are all the L functions in the world. I mean, this is not a theorem, but there's no other way of making L functions that anybody knows, global L functions, other than cusp forms on GLN. We took the general such guy, and we computed the n-level correlations, again with Fourier transforms restricted. We obviously don't go any further than Montgomery for the Riemann zeta function. And lo and behold, where everything is very complicated in our calculations, when we get the answer, it's always universally CUE. So this feature seems to be completely universal. Our aim was to show it was wrong. We were convinced then that this seems to be universal. So that's the universality of high zeros of any L function, not just the Riemann zeta function, seem to follow, at least in the computations of the n-level correlations in restricted ranges, are all exactly CUE. It doesn't explain why. It's a calculation that we're able to do. So this was then checked numerically, much like Odlyzko checked the Riemann zeta function by, I should say, a critical input in the proof. So the way we calculate this is to use the explicit formula. I call it of Riemann. Some people call it of André Weil. Other people call it of Guinand. They're all the same formula. It's a formula which relates the zeros, the sum of a test function over the zeros of an L function, to a sum of a transform of the test function over the sums of the coefficients and over primes. Obviously, primes are heavily involved here. And so you might say, what do I know about the primes? What do I know about the zeros? This is what we're trying to understand. The moral here is we are able to compute certain things with primes. We know the prime number theorem. We know certain properties of the integers and the prime numbers, sufficient to get some of these correlations. And to do it in great generality and show the universality, it turns out that there's a very important ingredient called the Rankin-Selberg L function, and its pole controls all higher correlations just by itself. So this is why it's universal. To us, this was quite shocking and changed our view completely. Numerically, this has been confirmed mainly by Rubinstein for different kind of L functions. The Dirichlet L functions was already checked after Odlyzko by Rumley, and later Rubinstein checked the zoo of different GL2 L functions. Every L function, wherever he computes the zeros, high up, there's only one answer, CUE, instantly CUE, perfect CUE, fitting like what you saw with Odlyzko's data. Okay, so we want to understand why, and this is what I'm going to try to explain at this point, at least some understanding. Now, if you look at one zeta function at a time, you might say, look, I'm not interested in anything. I'm interested only in the Riemann zeta function and in $1 million that you will get if you solve only for the Riemann zeta function. Apparently, if you prove the Riemann hypothesis for another zeta function, you maybe not get any money. You should read the fine print. I don't know why I read it. I'm nowhere near solving this. But if you read the fine print in the clay, it says if you disprove the Riemann hypothesis, they have the right not to pay you. Go read it. Then they'll decide. They have a panel that will decide. If you prove it, they have to pay you. But if you disprove it, then maybe it's too easy. You just hacked it away on a computer. I don't know. Some very strange wording there. It's not, let me fess up a little bit. It's not restricted to the Riemann hypothesis. It's restricted to all 6 problems. That is, if you disprove some of the conjecture, maybe the Hodge conjecture by some example, I think they're very nervous that maybe it's false, with some tricky example, and then which would force the reformulation of the conjecture. Okay, if you disprove the Riemann hypothesis, I think between all of us we'll come up with $1 million and pay. All right. So to understand an L function or a zeta function, experience shows that it's best to try and understand it in a family. It's extremely difficult to understand one function at a time. So I'm obviously not assuming everybody knows what an automorphic L function is at this point anyway. So let me just introduce some of the family of different L functions. So the GL1 L functions are just the good old-fashioned Dirichlet character. So instead of having the function 1, some n to the minus s, you have some chi of m to the minus s, and you still have an Euler product because the character, this is a Dirichlet character, is multiplicative. Chi of m1, m2 is chi of m1 times chi of m2. And it's also periodic. This is a very important property of this character. It must be periodic modulo q. So it's really a character of the ring of integers z mod q z star. It's 0 if you're not relatively prime to q. And these characters, this period, this smallest period, is called the conductor of chi. It is an extremely important number. It measures the complexity of the automorphic form of the character. It measures the density of zeros. If I want to look at the zeros now near the point of half rather than high up as I go over a family, these are going to play the big role. This conductor plays a very big role. So you have the L function. It's just like the Riemann zeta function. It's got a Riemann hypothesis, functional coefficient. Everything's the same. And also for an automorphic L function. That's something we know. These are not trivial things. Even for the Dirichlet L function, it's not trivial, but certainly for automorphic L functions. We know what we know for the Riemann zeta function for an automorphic L function, the basic analytic properties. That's why we look at the automorphic forms as the source of L functions. So here's a Dirichlet L function, and we might vary the characters in a family in order to understand even one of them. And that's certainly the way we proceed. And if any of you know the proof by Deligne of the Weil conjectures, he does not prove the Riemann hypothesis for variety over a finite field one at a time. He deforms it in a family, in a Lefschetz pencil, in the first proof. And it's all proved at once. The glue of understanding a family is used to understand one. And in analytic number theory, the deepest thing we know, the Bombieri-Vinogradov theorem, is a statement about families of Dirichlet L functions that the Riemann hypothesis is true for most L functions in a suitable sense. So families are really central. Let me look at the simplest family, because this was the first family for which the analog of Montgomery-Dyson was discovered. And that's, let me look at the Dirichlet characters of period Q, in which case we call them of discriminant D, because D must be square free and they correspond to quadratic extensions of the rational numbers, but they're just characters which are +1 or -1. This character squared is 1, and when it's 0, of course, I don't count it. So these are the quadratic characters, and what's important about a quadratic character, like the Riemann zeta function, the functional equation is back into itself. It's self-dual. The zeros are symmetric about the point 1/2, so the picture looks very similar to the Riemann zeta function. So now, just like we were talking about our random matrix ensembles, instead of looking at the zeros in the bulk, let's look at a family of L functions and look at the zeros near the point 1 and -1. The analog of the point 1 and -1 in those ensembles is the central point 1/2. And as we go along, you'll see the point 1/2 for an L function, the vanishing at that point, that's sort of the closest violation of the Riemann hypothesis, is a vanishing at a half. And you can vanish at a half, and you can vanish to high order. So it's a deep point, and that's the point at which I want to understand the zeros. There are no parameters in this theory. These conjectures that immediately emerge and which seem to be on a very safe ground by now are not based on any parameters, meaning I'm going to unfold, so I look at the zeros. Let me again assume they're on the line, so I'm looking at the Dirichlet L functions. Instead of multiplying by log of gamma or log of t when the zero is at high t, you multiply by log of the conductor when you low down. So there's something called the analytic conductor, which is the measure of the density of zeros. There's no parameters. You re-normalize in this way. There are no parameters whatsoever. And Katz and I, in our work in which we were forced to look at this tenfold way, I'll say a word about our work just because it motivated this. Our work in the function field suggests very strongly that the following is true, that these zeros here, as you go over quadratic L functions and any other family, whatever family is, should follow, in this case, some symmetry type that we compute in the book, and in this case it's a USP infinity. So remember, I had 10 types, and the first 4 are the ones that are going to come up over and over again in the theory of L functions, and this was the second one. The first one was the unitary, the second one was the symplectic. I drew you the graph of the lowest one for the USP infinity. This is the scaling limit. I'll say a word about our work in a second, but this was a prediction made, and Rubinstein was quick to check these. Everything is correct. So this is a prediction from that early work.
So you're distinguishing these from the bulk ones?
Yeah, everything now in a family. In a family, in the bulk, there's only one answer, and it's exactly the explanation, if you want, as you will see in a minute, of why Rudnick and I found that all L functions have only one answer in the bulk. But if you have a family, then as you'll see in a minute, we're expecting there are 4 universality classes and only 4. And they all come up, and I'll show you when and why they come up. Always a low, though. The low in the theory of zeta functions, always the zeros near half. This exact thing.
You're always at a half, right?
There's only, there isn't another point.
You're always at a half. The point is you're looking at the low lying.
The low-lying zeros of a family. And that's supposed to be, okay. So we predict the statistics of this. I want to be precise what this means. It's a very concrete prediction that you can theoretically prove, and again, you can compute and prove the conjecture, in this case, in certain ranges. Unfortunately, never in the full range. So I want to compute the n. I didn't write down the n-level correlations that Rudnick and I computed, but I want to show you the n-level correlations, densities for these zeros of zeta functions in a family. So you form these, you form the zeros. So the zeros are called gamma j chi d. I dropped the chi. So you sum over all, they come in pairs j positive and negative, so I'll sum over the j's, and the mod j's are distinct. So I don't want to count the same zero twice. Pretend the zeros are simple, just for this numbering. Otherwise, you have to put them in. Of course, when you prove anything, you can't assume it's simple. Phi is a Schwartz function on Rn. Rn.
So n arguments.
N arguments. You're taking n zeros at a time, all tuples of n zeros up to some size. So for each fixed guy, you sum over all the zeros. Because phi is Schwartz function decaying, the sum is convergent for a fixed L function. Now you sum these densities. This is the n-level density. You sum it over all your Dirichlet L functions with conductor up to x, and you divide, you normalize, you're taking the mean value. Divide by the number of such. And the conjecture of Katz and myself is that this should converge to the integral of phi, just like you saw with Montgomery and Dyson. But now the answer here is the n-level density for the scaling limit, which Katz and I compute using Godin's method, the scaling limit of the symplectic groups. So that is explicitly the following. It's the following n by n matrix. So it's a determinant of n by n matrix whose ijth entry is kxi xj, where k is the following kernel. This kernel is associated with a symplectic family. So this is a very concrete conjecture, and if you can prove this conjecture without restriction on phi, you've proved the low-lying, complete statistical distribution of low-lying zeros is that of the symplectic family near the point 1. Now, I should emphasize that if you're going to prove anything unconditionally here, you're going to have to arrive at some weird determinant. Where's that going to come from? From the theory of primes, out of nowhere will come a determinant. This actually was a sticking point for a long time, because you can actually compute this. And in fact, Rubinstein in his thesis was able to prove this, just like Rudnick and I were able to prove it for high zeros. He was able to prove this conjecture as long as the support satisfied that the sum of the that phi hat was supported in this L1 box of length of size less than 1. There should be no condition on this. Now, between 1 and 2, there's a phase transition here. This is a case where you can go quite a bit further, and a student of Sundararajan by the name of Gal was able to get an answer, a terrible mess, which he couldn't analyze and show. He could not show it was equal to the predicted answer, because that involves proving infinite set of combinatorial identities. But he got an answer. He overcame the analysis problem of computing using the techniques of this explicit formula and summing over the family. He was able to get this up to 2, but he could not verify the answer was correct. I say this because that's one of the things we've had some progress recently. Rubinstein, whose thesis is about checking these things and proving that, checked numerically, and here's the lowest. So if you take the lowest zero for the family of Dirichlet L functions, that's the most basic self-dual family in the world, and you look at the lowest zero, it follows the distribution that I told you that can be computed with Payne-Lavey, which is nu1 of SP, and this is for zeros of Dirichlet L functions up to about 10 to the 10. So not as far as Odlyzko went. That's a good fit. So it fits rather perfectly. You see the repulsion. I should say the repulsion was already observed by Hazelgrove, I think a student of Turing. So Turing, the minute he had his machines working in Cambridge, decided he wants to disprove the Riemann hypothesis. So he computed many more zeros than Titchmarsh and anybody before him. And he had the computer go up to a few thousand. Of course, all the zeros were on the line. Then somebody had a better idea. They said, well, if the Riemann hypothesis is false, it's maybe false for a Dirichlet L function for a zero on the real axis. So Hazelgrove computed the zeros of Dirichlet L functions with quadratic character very far out, with early, this is in the late 50s. And he found that the zeros were repelling. Nobody could understand why. Well, this is the reason. The distribution is the symplectic near the origin, and this is the distribution that this particular random matrix ensemble gives. Now, that's a completely different thing. It's a completely different thing. That's assuming Riemann's false. It's a completely different thing.
So how rapid is
This is not a big repulsion. This is at the scale of log. Yeah, it's completely different.
prediction for how rapidly these things are supposed to
Converge. The proof in there, when you compute the correlations and the numerics, is unfortunately all at the speed of 1 over log. So it's slow. There's a correction term, which is size log smaller. This is one of the many directions in when the subject is taken and people have put in, and after you put in those correction terms, then you might expect a power saving. This is already, yeah.
So there would be...
This is not following random matrix theory instantly. The main term is following it. There's a correction term which is arithmetic, not random, at size of 1 of log.
So you can maybe extract that. And then
Yes, there are a number of conjectures that have been made which were very unclear until that feature was incorporated, after which the fit became instantly better. But this is quite a robust statistic, so it fits quite well. All right. So the basic reason for this conjecture that we made, and at least the present understanding at the first level of why this might be true, is to look at another case, a different case, where the Riemann hypothesis is known and where we have a spectral interpretation to try and understand what is it that's the source of what you're seeing here as a phenomenological fact. So you replace the rational numbers by the rational function field FQT, which is operation first done by Emil Artin. So in that case, the zeta function of the field, or you're going to look at, I'm going to look at this quadratic family. So I look at all quadratic extensions of FQT here. FQ is a finite field with Q elements. And the zeta function is defined in the same way. I don't want to go through it. I'm not going to use any of this other than as motivation. But in this case, if you take a quadratic extension, the zeta function is a polynomial, not entire function of order 1 like it is for the Riemann zeta functions, a polynomial of degree 2g, where g is the genus of this extension. And its zeros are known to lie in a circle of radius 1 over root q in the way I've written it down. And that's the famous Riemann hypothesis proved by Weil, that all the zeros of this Artin zeta function are on the circle. And the question here is, what is the distribution of the zeros? Well, if I fix a quadratic extension itself, there's nothing to say. But what we were doing in the previous example was to look at all quadratic extensions of Q and look at the low-lying zeros. So you can look at all quadratic extensions of FQT and look at the zeros. Now I've normalized here on the circle, so the zeros near 1. And it would be lovely if we could fix Q and let the genus go to infinity. That would be the genuine real analog. But nobody knows how to do that. That's too difficult. So we do an extra averaging, which is the big cheat that Katz and I do, is we first let Q go to infinity and then let the genus go to infinity slowly afterwards. And in this double limit, we can use monodromy groups heavily, and the monodromy groups enter. We have to compute their scaling limits, and random matrix theory actually comes into the proof. It's not just an analogy, it comes into the proof. In particular, we use Gordon's methods, and we show that the typical zeta function, all the typical quadratic extension has its low-lying zeros follow exactly the distribution predicted by random matrix theory in this function field case. Of course, in this function field case, we have a spectral interpretation, thanks to Grothendieck, of the zeros on these cohomology groups. So we have the tools which we are missing in the other case and are desperately looking for. But this is all evidence we're trying to understand. And most importantly, we explained, this was why we were forced, we came up with these 10 symmetric spaces as the obvious places of where the random matrix theory was taking place. And the monodromy groups only scaled to give the type 3 family. And so only those come up in the function field. That's a theorem. The distribution of the things will always follow one of those 4. And in the bulk, it's always universal. For those four all collapse to the same CUE, completely explaining in the function field the phenomenon that high zeros of any L function are CUE, and the low zeros only come in 4 families. So that's understood in the function field completely. Modulo the big cheat of first letting Q go to infinity. If I could fix Q, it would be probably as hard as the problem. Even though we know the Riemann hypothesis, it would be as hard as. So it was based on these function field considerations that we turned back to the number field and made all these conjectures, which were then checked numerically, and everything has been fitting nicely into yeah. So that's the end of my historical review. And I now want to explain why is it that, and this is only recent, why is it that these 4 come up, and only these 4? So high zeros, there's a universality. Low zeros, there are only these 4 that come up. So the question is, can you actually prove that it's one of these 4, and what do you compute to see that it's one of these 4? And this is a paper that was just put on the archive by Shin Templier and myself, which firstly gives a definition of a family of L functions, a completely general definition of a family of L functions in the automorphic case. So in the number field case, in the algebraic case, a family usually means a family of varieties varying over a base. There's a well-known how to define families. And then monodromy usually is how the cohomology varies as you move around in the family. Unfortunately, in this number field case, the set of automorphic forms is countable. So you can't make a continuous deformation. It would be lovely. But in the function field, you can make a continuous deformation in the sense that algebra, it forms into a family. In the number field, we make a definition, and there are two forms. So I should say that after this work of Katz and myself, there have been slews and slews of papers verifying these conjectures in ranges numerically for different families. I've always wanted to, and that's what's done in this paper after a lot of false starts, to make a formal definition and exact predictions, completely falsifiable. And in all the constructions of all families, there are only two ways of making families of automorphic forms over a number field that have ever been attempted. And these are, and that's the definition. They are either through harmonic analysis. So an automorphic form is actually an eigenfunction itself of a ring of differential operators. It's coming from representation theory. And you can use representation theory and Weil type laws to count and order automorphic forms. They're countably many of them. So we call this a harmonic construction. That's one way of making a family. And the second way is conjectural, but is not conjectural always, so it's standard conjectures. That is, you take a genuinely algebraic geometric family of varieties, smooth projective varieties. It's absolutely important that the base here not be complicated, something like projective space. So I have a family of algebraic varieties, and for each algebraic variety, now this family is well defined algebrogeometrically, it's defined over Q, and for each one of these I compute the Hasse-Weil Zeta function on a piece of cohomology. That's an L function which is supposed to be modular in complete generality. And this would, in that way, produce for me a family of L functions, and these L functions are supposed to be, those are the second kind of family. So these are two families. And the question is, what controls the distribution of the zeros? Even if we don't know that these things are modular, we can even entertain it, but certainly in examples where we know these give automorphic forms, we can look at this question. And there's a very important thing that intervenes to answer these questions. Firstly, so if you have a family, you'll have these set of automorphic forms which are defined in the way that I just mentioned vaguely. I didn't explain it clearly. You'll have to look at the paper for that. Anyway, whichever way you slice it, you have a set of automorphic forms, and they are always ordered by their complexity, by this analytic conductor. That's the way you measure the zeros, how you renormalize to see the distribution. So if you're ever going to make any progress, there are two things you would absolutely need to know, is how many elements roughly are in the family whose conductor is less than X. It's not difficult to show using automorphic forms that the set whose conductor is less than X, the universal set whose conductor is less than X is finite. And you would want to understand in your family how many elements there are. And if you write the zeta or L function in a series or in a product, you would want to understand what is the average value of the coefficients as you vary over the family. These are two things you should at least be able to compute. And these are things we can compute in these definitions, always, and I just want to tell you what the source of that is. These are not easy computations. For the harmonic families, it's always done through the trace formula. The trace formula converts for you something about the coefficients, about the Hecker eigenvalues, in terms of conjugacy classes, and then you are facing something you can try compute and compute averages. So that's done in all the examples. The case of Dirichlet characters, you don't call it the trace formula, you're just using the orthogonality of characters on an abelian group. So it's like the most baby trace formula. In the algebraic family, the distribution of these numbers that I just put up here, this kind of thing, can be computed also. And this uses finite fields. So you reduce mod p, you show that the lambdas only depend on things modular p. And then you're in the characteristic p world, you can use a technique Same technique that Katz and I were using, these equidistribution theorems connected with monodromy of families due to Deligne and Katz. And then there's this explicit formula which allows you to go from there to the zero. So this is always the procedure, and this is the procedure that's been followed, and the low-lying zeros have been computed for many, many different families, always consistent with these conjectures, though nobody had a way of predicting what the symmetry type would be, and that's something that's new. So I want to end in the last 10 minutes, as I said, with two things that are new and which played a big role in making this definition, or vice versa, I should say. The first is something which is very similar to something called the fundamental lemma. It's about a proof of algebraic identity. I told you that Gao was able to prove that just for Dirichlet L function, something very concrete and simple that any 1970s analytic number theorist would be happy with, you could compute the low-lying zeros was what it's supposed to be for all the n-level correlations, not for the support up to 1, but for the support up to 2. But he couldn't show that the answer was given by this weird determinant, because that involved proving for every n a new identity. And there may be, somebody may be very good at combinatorics, may be able to prove the identity. In fact, I should say that when Rudnick and I wrote our paper, we were stuck for 6 months on proving a related identity. And finally, we found a combinatorial proof of it. And it's much better if you have a conceptual proof. And the conceptual proof is that this is one of the things that you can reduce to the function field. Very much like what's called the fundamental lemma. If you have a combinatorial identity, maybe if it's true in the function field, you can push it over. And that's an observation of Enton, Rodity, and Rudnick. It's Rudnick and two of his students, both of them are just finishing this year, to show that for the original, their main achievement in this discussion here is to double the range. So they didn't do anything new in terms of analysis or in terms of what you can compute. They just showed the answers what it's supposed to be. In the full range, -2, 2, and it's gone through a phase transition. The answer changes at 1, the nature of the answer. I don't want to go in. And the way they do it is they take the same calculation in the function field and they don't use all the techniques that are available yet. They take the same techniques that we're using in the number field where we don't know what Frobenius is, we don't know the spectral interpretation, but we do know how to compute traces and averages. So they do the same calculation in the function field for FPT and quadratic extensions. The case that I said, if P gets large, we know what's happening if we average over P. And they get an answer, and the form of the answer that they get is structurally identical to the form that you get that Rubinstein was facing and Gao. And so the identity you have to prove turns out to be the identical identity. So they just need to then use the work of Katz and myself. After checking that this is uniform enough, they're able to average over P, invoke the fact that if I average over P, the answer is what it's supposed to be, to conclude that the answer is, they prove the sequence of identities in this unusual way. It's the second time I've seen, not usually when you go to the function fields, an analogy. It's unusual when it's actually used in the number field proof. That's certainly true in the fundamental lemma. Gao proved it in the function field case, and there's a transfer principle of the identities to the number field. And it's all, and the fundamental lemma is also just a combinatorial identity. So it seems combinatorial identities that might come out of these kind of trace formula calculations, which is where this comes from, and this is just GL2, GL1, even GL1, might be very complicated combinatorial identities, and the function field somehow allows you, because there we have the group and the monodromy groups. The second thing I wanted to mention is a beautiful paper of Shin and Templier, which concerns harmonic families. So those of you who aren't in automorphic form, just ignore the next 3 minutes, because this will be meaningless. But they looked at a rich enough family of L functions so as to actually start to guess what the true answer should look like. What's the source of these 4 universality classes? So before, the examples we were looking at were elliptic curves, number fields. These were all a little simplistic, and somehow none of us saw the picture. This is a sufficiently rich, and they quickly saw the picture as to what the answer should be. So they start with a reductive group defined over Q. Its Langland's dual group is how you parameterize the L functions. and a representation of the dual group. This is a finite dimensional representation into m by m complex matrices. And Langland showed how, starting with this, and given an automorphic form on the Abdel group of G, so as I said, if you don't know what I'm talking about, ignore this part. I'll be back to the world of ordinary mathematics in a minute. I know that in a general audience talk, the minute you say Adels, you get shot. But it'll just be for the second because I can't lie as to what it's about. So you have an automorphic form. There are these countable number of automorphic forms, and you can form an L function that Langland showed how to do. And that L function is supposed to be an L function after functoriality on GLM. So this is one of the ways of harmonic method of making automorphic a family of L functions. It's a very rich family because you could start with an arbitrary H, as I started there, and an arbitrary representation rho. And in many cases, these things are proved, so these are concrete examples. And what they showed is they computed the one-level density using the trace formula. They assumed that the pi at infinity is discrete series. This makes the trace formula much friendlier. So the analysis becomes algebra, and they can do it. And they found that the symmetry type is either the four types that are that we discussed. They don't break into even and odd, depending on one number. And that's what's the unifying feature here. You have a representation of the dual group into GLM. Now, when I have a finite dimensional irreducible representation of a group, there's something called the Schur-Frobenius index. It tells me whether there's an invariant. This is all finite dimensional, nothing infinite dimensional. It tells me whether there's a bilinear pairing which is symmetric, bilinear pairing which is anti-symmetric, and whether there's no bilinear pairing. And it's computed by a number called the Schur-Frobenius index. And this Schur-Frobenius index dictates exactly the symmetry type once you compute the low-lying zeros. So they explain the answer very beautifully, that the symmetry type is orthogonal. So if the Schur index is 0, then the symmetry type is U infinity. If it's +1, it's SP infinity, and if it's -1, it's O infinity. So this was a rich enough family to have a universal answer to make us believe that we know what's supposed to happen now. And that's what's done in this paper of the three of us. There's firstly the definition, which is something I'd been working on for some time. There's a definition of a family, and in each of these cases, there is a construction which in this example is straightforward from something called the Plancherel density. And in general, it's computable. So the distribution of the lambda pi t's as you go over the family, which you have to be able to do, and I said you can always do. We have the two tools to do that, the trace formula and the Lee and Katz theory. These allow us to determine a subgroup. We call this the Saito-Tate subgroup associated with a family, which has all to do with the coefficients. So I told you the coefficients are highly non-universal. These Saito-Tate groups can be absolutely anything. But they have a unique Schur index. And they have some other indices also associated with this. And those indices dictate the symmetry type, and provably so, as always with restricted ranges. And there are only 4 types. So it works out that this is the universality of the low-lying zeros. It fits into this 4-fold way that the function field predicted and seems to be true in the number field, at least in the generality of the definition that we give of families. I have one more slide, I think. I've not done justice to the many things that have happened in the subject. These theory of families of global L functions lead to many unconditional theorems. You might have heard from the beginning I'm saying assume Riemann, assume Riemann. After a while, you start dropping that, and you prove things without assuming Riemann with these symmetries. Some are conditional on Riemann, some are not. And let me mention 2 high points. One is the work of Keating and Snaith, who explained in terms of the random matrix theory and these symmetry types that I've been explaining to you for families, what the conjectured moments in family should be. They have a beautiful conjecture, and there are some data points which fit perfectly. And this is a good example where we now have numerical evidence after fixing up correction terms. The point and a half is by far the most interesting for the theory of L functions, because the vanishing there is connected with ranks of Mordell-Weil groups. So there are tremendous applications to Birch, Schmidt, and Dyer, to unconditional theorems. The families are also the means of proving subconvexity and approximations to Riemann. I mentioned the Bombieri-Vinogradov theorem. So what we have here is a glue, which is obviously there, which is gluing the different things with the right symmetry types, which we now understand, but we've never explained it properly. So I want to end what's really lacking here. But with the minute you understand this, you'll understand everything. And that is the real reason that these families have these symmetry types has to be like in the function field, that each of these operators, each of these zeros, when they're given a spectral interpretation, the operator presumably will preserve one of three non-degenerate pairings, which will tell you the symmetry type. But until somebody has a very workable or useful spectral interpretation in the case of number fields, we have to work backwards with all this evidence that's accumulating that does come from random matrixing. That's all I know. Yes.
Suppose you can prove all this stuff about statistics of zeros, of various L functions and so on. What can I now learn about prime numbers?
Oh, okay. You could learn much finer questions about distribution of prime numbers, but you could learn much more. So the vanishing at a half. So if the statistics is what it should be, then the vanishing at a half will tell you where, so you take the family of all elliptic curves, it'll tell you that half the elliptic curves have rank 0 and half have rank 1. There are some recent results which approximate that, mostly by Ankar and Bhargava, but this would give you the complete truth as to things like that. So in a family, the number of times you vanish at a half is measuring something extremely relevant in the theory of numbers. For me, it's a different reason to look at this. I believe this, if I ever want to prove something about a given L function, and it's much more modest, not Riemann, some non-trivial estimate, something called subconvexity, this tells me which family to deform it into to try get such an estimate. In other words, this will quickly predict what the answer should be. So this is an extremely powerful predictor. If you want to know what the answer is, and maybe you say, all right, if I could compute this, is this going to actually give me something unconditional? This will tell you what the answer is going to be instantly. And it's used like that all the time. To make things completely unconditional, like a non-trivial estimate, you can't assume Riemann. So I said that these actual distributions are what they should be, and this is unconditional without assuming Riemann. But if you're trying to control the zeros and they're off the line, and you're only allowed to use test functions of a certain type, you will actually, it's very hard to use this. So the upshot is, it's my hope that the symmetry will eventually be the real test. So to me, it's, if you look at the proof by Deligne, let me repeat. The proof by Deligne of the Weil conjecture is very different to the proof by Weil in the case of curves. In the case of curves, Weil gave a proof one zeta function at a time. And nobody's ever given a proof in general without taking a family and using some statistics in a family through monodromic groups. Any progress we've made for one L function is come through families. So I believe the families is even more important than the spectral interpretation, because it's already giving many unconditional results. But of course, some of these things are conditional. So some of it is used, some answering at number of levels. Some of this is used as a good predictor. Some of it is used then to take the same calculation, but where you don't take the logarithmic derivative of the zeta function, because that's when things become unconditional, but the function itself. So one can prove the ranks of J naught n, this Ivanic and I, and Van der Kamp is sitting in the back there. I only see him once in a while, but his thesis proves that the rank of J naught n, if I remember, is what, bigger than 1/4 times n or something? He can't remember. Unconditionally, but that's a family calculation. Yeah. No. Good question. Been asked this many times, and I'm very defensive about it. The question was, is this the theory of the functional equation? In other words, can you see the symmetry type merely from the sign of the functional equation, which would be very disappointing? The answer is absolutely not. The examples where the sign is +1 and the symmetry is quite different to what you expect. So it's not. There are some necessary conditions. If you're in certain families, the signs, so if you have an orthogonal family, the Sato-Tate measure, which I didn't explain, is orthogonal, then the sign has to be +1. So there's certain cases in which you can actually say the sign dictates the answer, but not in general. This is not a theory of the sign.
So for the quadratic,
For the quadratic, it's always +1.
that's a coincidence.
And you can, in odd dimensions, you can tell from the sign. So that's a case where you can tell, but in even dimensions you can't. And this is the same. If you look at these insulator things, they're pointing out certain symmetries can be seen through time reversal, charge reversal, and then they look at the combination of the two, and they come up with the same 10 families just with 2 pages of calculation. No Cartan. And of course, this is shown to be the exact same as Cartan's family. So some of these have internal consistencies in which the sign plays a big role, but it's not the theory of the sign. Yeah. Yeah, he's got a question. Yeah, so they're really, okay, this is an excellent question. They're really only 10, so if you look at my paper with cats, we say they're 11. Nobody else says 11, because we took the orthogonal and we broke it up into 2, because we look at SO even and SO odd because of the sign of the functional equation. So if you first determine one of these 3, and then when you're in the orthogonal case, the sign of the functional equation, which is a separate input, tells you about this breaking into even or odd orthogonal, and it plays an important role. You can have families where the sign is +1 throughout by force. So the pure families are in our calculation with cats, where we compute these distributions. We break up into those which are SO even and SO odd, making 11 families. But if you look at any physics, it'll be part of 3.